So we're done the order epsilon calculation of critical exponents. What an ordeal. How long was that? We finally have a non-zero alpha. That's nice. You know what eta is? The anomalous dimension of the order epsilon. It's still 0. It doesn't get contributions till second order in epsilon. So even though I tortured you with that anomalous dimension, it still doesn't show up here. Let's see. Let me just, I think the numerical values are interesting. So you have epsilon here. So if you want to look at 3D Ising, remember epsilon's 1 in that case, right? So you'll calculate the 2D exponents on the computational assignment because it's computationally easier. Like it's one less dimension, right? So for 3 dimensions, let me just write them. So I'll do the exponent. Let's see, order. I'll just plug in this. Remember mean field theory, and then what's known. I'm going to talk about how these exact calculations are done. So 0.167, that's alpha. 1.167 for gamma. So remember mean field, alpha was 0. God, you should almost have these memorized by now, right? Delta was 3. Nu was a half, right? A half and 0. So again, mean field theory, these exponents, exact in 4 dimensions and higher, right? So this is the 3-dimensional ones that we've just calculated. And I'll talk more about the accuracy of these exact results, just to remind you on some of these. So let's see, gamma is 1 point. This one's been updated recently, 7, 4.82, 630. 0.032. Okay, so that eta, we still haven't seen a non-zero eta actually. Like I said, you need this at least second order in epsilon, but that's the value known for 3D. Otherwise, I mean, the accuracy is not great, but it's not terrible. You know, you would imagine going to higher orders in epsilon and doing this calculation to improve the accuracy. So let's talk about higher orders and epsilon, but let's go back and also talk about, you know, we're generating higher order couplings when we did these Feynman diagrams, and I promised you I would talk about that.
Do you know the exact exponents for 3D?
No.
But then what's that exactly?
Exact numerical.
Numerical?
So traditionally they were calculated with series expansions, typically. Monte Carlo, like what you guys are doing, used to hold the record for most of these. Like I've left off some digits. But conformal bootstrap, which I'll talk about now, holds basically the record
So
for.
there's a consensus about that value.
Yeah, there's consensus on these values, and some of these are known to how many decimal places? I don't know, I wrote it down somewhere. 1, 2, 3, 4, 5, 6, 7, 8 decimal places.
Okay.
Yeah, so some of these are highly, like very, very accurately known, especially for 3D izing. Okay, so we'll talk about that accuracy. Okay, we can do that first. We'll talk about the irrelevance of interactions later. So, how do you get higher orders in epsilon? Okay, so the way we set the calculation up, you would calculate all these diagrams. So these are one loop calculations. There's one loop in the diagram. You'd have to calculate diagrams with higher and higher loops, which gets actually way, way harder. 2 loop calculations are pretty hard, and people go up to six loops. I don't know why, but it happens. People do it. One thing I glossed over in that entire calculation was, if you look back, the RG recursion relations had the big, lambda in it, which was the UV cutoff, right? So in principle, that's disturbing in some sense. You shouldn't have cutoffs, even though it's whatever. You just basically shouldn't have these cutoffs in the universal quantities. You don't want the universal numbers to depend on the cutoff. At some point, I just started writing that as a constant. But in principle, that's not really a constant. So there's actually, better schemes or more advanced, I don't know. So no one really uses this Wilsonian momentum shell to go to these higher and higher orders. But these, there's these different, you can read about these in books. Different schemes of these calculations analytically basically don't make as much sense, if you can imagine that. Right? So at least we can logically kind of go through how the RG is constructed and the framework for the calculations and the idea of decimation over the fast modes and so on. But these avoid including in the, say, recursion relations. So if you're actually going to do this for a living, you would do a slightly different type of technique. So I just wrote down some, it's still an epsilon expansion. Like, you're still getting the same equations in the end, but you're just handling this idea of the cutoffs more carefully. So I'll just do one exponent. I just wrote down 1. So the 0th order in epsilon, alpha, beta, gamma is 1. And then I'm adding epsilon over 6. That makes sense? Yeah, okay. 0.167. One, two, one. That's squared. Oh, it's minus the next one. So that should disturb you. It looks like things are going the right way here. You get a nice correction. That correction gets smaller. It gets smaller again. And then all of a sudden it starts getting bigger, all right? So if you just add up all these contributions, So you have order 1, you know, you go, wow. I don't know how to write this. So you start with 1, then 1.167, 1.244, I just added these up for fun. Right, so is that what I wrote up there? That's gamma for first order and epsilon. Then it looks like it's maybe converging to something, what's the exact 1.237? Looks like it's getting closer to third. So people probably, you know, thought they were doing pretty good. All of a sudden, it just goes wacky. That's just what the epsilon expansion does. So did we do it all for nothing? Remember when we did Gaussian fluctuations on the Landau-Ginzburg-Wilson theory? We also had kind of an expansion, a perturbative expansion that didn't work. Remember the U was growing and we had all sorts of problems with that. In this case, it's okay because it can be proven. That these expansion coefficients obey what's called an asymptotic series. Okay, so if this is the power P, so for epsilon P, epsilon to the P, the expansion coefficient, I'll call it F, some constant P factorial, some number to the minus P. I'm just telling you a fact. I'm not going to tell you why this occurs, because I don't know. So it's just some deep result in basically, you know, field theory. So even though this expansion here isn't convergent, you can rewrite this with what's called the Borel summation method. Or reevaluate, I guess I should say, because it. And you just use some identity. I want to write that factorial. So then the expansion coefficient as a function of epsilon is summing up, right, all the powers, for epsilon to some power. Okay, so this is my quantity. Let's see. So I can rewrite this as an integral over a sum epsilon x to the p factorial. And this final sum here is convergent. Borel resummation. So it's convergent, results in a function. You just got to integrate that function. And that's how these higher order and epsilon calculations actually have to be done. So I think this is beyond the scope of this class. But just so you know, you don't believe somehow that this type of naive expansion is enough. Actually, you need kind of one more step to really do this to any precision for higher orders in epsilon. Okay, so that's just, if you ever hear Borel summation or asymptotic series in terms of these types of interacting expansions, that's the point. Somehow there's this resummation which is required. So if you do this, I have the value for the 6-loop calculation. So we did, like, again, 1 loop for the second cumulant. You keep going higher and higher and higher until you get 6 loops in your Feynman diagrams. Then that Borel summed value for gamma, which somebody did. I don't even have the citation. Gives 1.2405. A lot of work goes into that. Not only do you have to wrap your head around this asymptotic series, you have to actually do all these Feynman diagrams. People did it. I don't know if people do it anymore. So you can actually compare this to a numeric, I think. Okay, before a couple of years ago, I have a value for a series expansion. So it's body-centered cubic. So numerical. So these things are pretty accurate. 1.23, oops. 2375, error bar 6. That's the error in the last digit. That's the error in the last 2 digits. Are they consistent with the error bars? Almost. Who knows what that error bar means, right? Who knows? Anyway, nobody does this. Nobody would do this anymore. People did this, but even the numerical simulations, in principle you can, Monte Carlo, you have to increase the number of Monte Carlo steps, and the error bar shrinks as 1 over root of that number. So even those battle, they battle this, this sort of slowish convergence. But since, I don't know, probably since 2008 or so, the record for calculating these especially in the 3D Ising model, the 3D ON models, like stuff you guys have been working on. They've come from a non-perturbative I would call it like a meta theory. It's like a theory of theories. It's a theory of theoretical, like the mathematical structure of theory space. I don't know if I should, am I being recorded? Meta? Called the conformal bootstrap. There's experts on conformal bootstrap in the building. It's non-perturbative conformal, so scale invariance, dilation symmetry is what it's called. Because when you dilate the system, you have a symmetry. There's no length scale, so things look the same after dilation. So dilation symmetry in one dimension implies what's called conformal symmetry. Conformal symmetry means you can deform the lattice in a way that you preserve local angles, say. So conformal field theory is the consequence of that conformal invariance. In dimensions higher than 1, it's only conjectured that scale invariance implies conformal invariance, but many people believe it. So, like, D equals 3, D equals 2 Ising models, you could rewrite this type of field theory in terms of conformal invariance in a CFD. And with that conformal invariance, this non-perturbative bootstrap method lets you calculate, or to high accuracy, at least get a bounds, a very highly accurate bound on many of these critical exponents. So the conformal bootstrap, I don't have a citation for this either, but value for gamma is that 237. Yeah, so I'd say the numerics was closer. I would say that. I mean, this, again, you've conjectured, maybe? Conformal. So conformal bootstrap's interesting. It's, there's a lot of work on it here. I wrote down a couple. There was their colloquium in January, which you can watch. The colloquium starts just talking about scale invariance. It's like this. It starts with this class, you know. David Simmons Duffin. This is on Pearsa. I got the number 170-182. That's worth watching. It's cool. Like I say, he'll start with what's a phase transition. He'll talk about scale invariance. He'll talk about, you know, continuous second order transitions, I think he calls them. Then he'll talk about this sort of modern landscape of conformal bootstrap and how it's like a theory of theories and where the 3D Ising, you know, critical theory sits in this sort of higher dimensional space of theories and so on. So yeah, that's, and I say it's non-perturbative. So you get these bounds, but it's not like doing a perturbative expansion. So maybe you're wondering why I taught you this. Well, you know, why did we do this for months? I think still, you know, this is the intuition, the epsilon expansion, the idea that you have the, you know, just the idea of the renormalization group and that you can do controlled calculations. This is the theoretical framework for all of our intuition behind these types of problems. So I wanted to still talk, you know, we can't escape. Any questions on this stuff?
And then can we consider that as an exact solution if only if the conjecture can be proven?
You need the conjecture to be proven. I think what people would say is that the fact that this, say, matches the best series or the best classical Monte Carlo estimates is evidence of this conjecture. I think people would use it the opposite way. Because if you do a simulation like you guys are doing, you're not assuming anything about conformal invariance or otherwise. So actually people are using simulations to make sure that, so there's probably a more accurate Monte Carlo value than this. I just couldn't find it. People are using those simulations to test. Now they're saying this is a test of whether or not the 3D Ising model is conformally invariant.
This is not simulation.
This is this conformal bootstrap. But it's the most accurate, you know, assuming it's the most accurate value we have numerically.
And then can you say at least exact solution exists for 3D Ising model?
No, it's not exact. It just gives a bounds. It's not like an Onsauger solution that's exact.
I'm thinking about existence. Some people say, oh.
I'd say it exists. The 3D Ising model exists. But, I mean, what does an exact solution mean, I guess?
There's a difference between it exists as in an abstract atomic setting versus it exists as in here it is and somebody's written it down. So which do you mean?
Yeah, I don't know the difference.
One solution.
Right.
I would say not. I'd say that solution doesn't exist.
Right.
Yeah. But
So
in the solution space of solutions, there's a point that corresponds to the 3D Ising model, and the conformal bootstrap gives you.
I heard that some people claim that they proved non-existence of the numerical solution for 3D Ising model, but I couldn't fully understand what does that mean.
Yeah.
Maybe in closed form?
I don't know what it means for us. Yeah, it's a good question. There's definitely no closed form solution, but I don't know if you can prove it doesn't exist.
Genius, did tremendous research on it to find one second like this complete solution for 3D, but nobody did. So
Watch this guy's talk. He's a modern. This is like a month ago, and he's an expert, and he'll tell you what's known and what's not known about this space of theories, I think.
I mean, given its resemblance to quantum channel theory, a lot of results in that are not known in those formulae aspects.
To mitigate your disillusionment a bit, at least let's talk about all these phi 6 terms and stuff we threw away. You know, we constructed a phi 4 theory essentially microscopically, if you want to believe that, from Hubbard-Stranovic and so on. But you can also just look at the action, like the phenomenological action for the Landau-Ginzburg-Wilson, theory. And in principle, you should construct that action, to be, I don't know, there's different conditions you might want on that thing. It's well behaved and it's, physical in some sense, and it obeys all symmetries of the problem. So this issue of symmetries is important because, why stop at phi 4, 5 rotational symmetry or something like that? Why not go to all the even powers, ad nauseum? Why not include, I don't know, the other gradients that we didn't include? So just a symmetry argument would, never mind the fact that we're generating, we are generating all these other interactions, but if we included right from the start all the phi 6 and phi 8 and everything like that, we would just be renormalizing the couplings of those. So why don't we need all of those in the theory? I wrote some down. Let's keep a zero field so we don't have odd terms. So, and let me write this action. So you still have a Gaussian piece that in principle you can solve with Gaussian integrations. And then an interacting piece. For us, that was just a phi 4. But with higher order terms, my gradient, phi squared. Now I can have terms that couple. Or higher order gradient terms. I got terms that couple phi squared in the gradient. And in the interacting piece, it would look like, let's see, my phi 4. So this one's an interacting piece, actually. I'll call it V, and then you can have U, I guess 6, 8, forever. So you can do the rescaling and look at the scaling dimension And if you did that, you'll get things like things that we know, like the equation for R. But you'll get all these equations that are like R was B squared. Or if you write in differential form, what happens with K? K prime is always, that should be implies. You'll find it always scales like that. This higher order Gaussian term, you find goes like this. That's the Gaussian pieces, the interacting pieces. So U, we already calculated that one. So the differential equation, 4 minus D, so that's your epsilon. V, that's the lowest order coupling between phi squared and the gradient. That one goes 2 minus D. So it's minus 2 plus epsilon, right? So I'm just putting in my epsilon there. And importantly, those 6, so you use 6. So du6 over dl minus 2 plus 2 epsilon. I'm writing them like this so that you can see what's relevant and what's irrelevant as a function of epsilon. 8 minus 3d. We're doing partials. 8 minus 4 plus 3 u8. Okay. I guess you could plug in the dimension there. So even if you have all these couplings, and there's more, you can keep going. You'll see the pattern in the higher order couplings here. You'll still just find 2 fixed points. One's a Gaussian. So now it's R and L and U and V equals 0. You gotta keep you gotta keep K non-zero. Or else, I don't know, you don't have a theory. So when you have eigenvalues, or scaling dimensions, YV, YU6, I'll call it 6 for U6. Gaussian fixed point already had a bunch of relevant interactions, right? Epsilon's positive. Where's R? Okay, this one's irrelevant. This one's irrelevant or marginal. So you see what matters and what doesn't matter. You still have a Wilson-Fisher fixed point. It's just generalized with all these couplings. So R U. That's the Wilson-Fisher fixed point. That's what I'm saying. It's not 0. It's order epsilon. What you find is, let's see, L, V, these become order epsilon squared. So they're like perturbatively closer to the Gaussian fixed point. And I think U6 is higher order, epsilon 3. And the scaling dimensions are the eigenvalues. With order epsilon corrections. Is that what we found before? Yeah, I think so. Y6 minus 2, Y8. So in particular, these higher order phi 6 and phi 8 interacting terms, you see they're getting more and more negative. Right? So your relevance is really restricted to just one, if you want, just one sort of direction. Or 2 if you have a field. So just keeping in mind that the eigen, okay, so the RG axes, which are the eigenvalues, they're rotated away by that linear transformation. I mean, they're rotated away from these exact axes in principle. There's still only one relevant direction associated with t, y of t, or r, whatever you want to call it. So we had this RG flow, but now we're in this higher dimensional parameter space. I don't know. That's all those other dimensions. Here's your Wilson-Fisher. You have one relevant direction because yt is greater than 0. So whatever that axis is. What did I say? It's relevant? So that's yt greater than 0. And then everything else is irrelevant. So you just have things that are flowing in that higher dimensional, you know, whatever these things are, yi's, they're less than 0. So that whole space of irrelevant directions is called the basin of attraction. So the universality of exponents is basically traced to that basin of attraction. So even though you can have all sorts of couplings, maybe in your microscopic theory, if you did the Hubbard-Sirtanovich with all these couplings, you get all these higher order terms, that we just kind of argued for by symmetry. So even though they all exist, and you can't ignore them microscopically, you get only a few universality classes. And the universality classes depend on, like, basically now you see them, they depend on the symmetry of the degree of freedom of the field, right? So if it's Ising-like, if it's O2, if it's O3, that'll change things. It depends on the dimension. And it depends on, so symmetry of the order parameter, invariance of the interactions of the Hamiltonian, and the dimension. Basically, that's basically it. And everything else, all the other interaction types and so on, they just add another dimension to this basin of attraction. And whenever you're crossing, you know, one of these planes, as you change some parameter like temperature, then the physics of that phase transition, well, the physics will always flow in this RG sense to that Wilson-Fisher fixed point. Okay. So that, I claim, explains universality. I guess I should really just end the class here, because how could you beat that? Okay, I think that's enough for epsilon expansion. Questions on this? Make sense?
You need to do the calculation to prove the point.
You want me to do all that?
No. No. You like one needs to do that.
One needs to do that. Yeah. But you see the trends in higher order, especially the higher order interacting terms and so on.
Yeah, something like that. Actually, like,
well, so that's a separate thing. The Borel summation is, yeah, I mean, in principle, you need to do that Borel summation for all of these things to show that they're not turning positive. So hopefully somebody did that at least once. So, but yeah, usually the Borel is just used for trying to get more accurate critical exponents. Although, like I say, nobody uses it anymore. So speaking of different theories, what we're going to do now is move away from the Ising model. So, you know, it only took 2 months to talk about the Ising model. You know, you get different types of fixed points in different models. And these long wavelength theories, so one of the points of this type of RG procedure is also that we've justified going to a long wavelength theory in some sense. You know, we started from some microscopic, you know, Ising model. We've gone to some Landau theory. So we're going to look at different long wavelength theories. And from this, it seems like those long wavelength theories, like with this symmetry, you know, this is enough to describe all the phenomena that we're interested in terms of phase transitions and matter. But it turns out, which is what we'll work towards, is that in 2 dimensions for an O2 theory, there's a kind of like a hidden phase transition that isn't part of this kind of long wavelength framework. That's called the Kosterlitz-Sallis transition. That's what the Nobel Prize was for this year. And so to see that the Kosterlitz-Sallis transition exists, you basically need more than like that type of action. You also need to consider topological defects basically in those fields, in the phis. Okay? So that's what we're going to work towards now. And so what we're going to do is we're going to basically start from like an ON continuous symmetry field theory like that and see where this topological defect issue arises. So So we'll move beyond single component or scalar phi-4 theories. You've already done this on assignments. And we want spins that are vectors, as you know. These are physical. The idea that you have ON symmetries are physical for things called Heisenberg models, for example. A Heisenberg magnet would be something that I think I would just write as this. I guess I'll do it in general. Jij S I dot Sj, right? So that'd be an O3. Or a full three-dimensional space, or a three-component vector. So S, Sx, Sz. Ising's kind of just a special case of that, where you only have one spin component. And xy is this special case where you only have two. That would be called easy plane sometimes because your rotors are in the plane. Ising's called easy axis because you're on the axis. That has O2 symmetry. I think you've already derived the Landau-Ginzburg-Wilson functional. Or we've at least been using it on assignments. So what we're going to derive from the Landau theory is something called the nonlinear sigma model, which I've given you RG recursion relations for on this assignment 4 that I'll give for you today. So we're not going to derive them in this class. We'll derive the nonlinear sigma model and talk about it. But I'll also give you the chance to look at how the RG recursion equations look for this case. So hopefully this looks familiar. I gotta start writing things as vectors. Let's do repeated indices summed over. A, maybe? Do I need a dot there? I don't think so. Okay, that's like a gradient term. We'll use R. And again, the dot product is the scalar quantity that we write for this theory. And yeah, so it's only this case where repeated indices are summed over. Okay, so that's I guess what I call the ON model. So just some features of it, like the Ising model, when you have these vector spins, you have an upper critical dimension where the mean field theory, say, works or gives you the right exponents. And so just like the Ising theory, in this case, the upper critical dimension again, where mean field theory is valid, is D equals 4. But, in principle, the critical exponents are different than Ising. So they might depend on this ON symmetry. And there's an important sort of caveat to this idea of dimension. There's actually what's called a lower critical dimension that we have to worry about for these ON theories. What's the difference? What is a lower critical dimension? The lower critical dimension we've already seen. I don't think I called it that. It's the dimension below which the phase transition disappears. So in the Ising case, we actually already saw this. We already argued from many different perspectives that there's no Wilson-Fisher fixed point. There's no like Ising phase transition in one dimension. I mean, I think the nicest thing was looking at the RG flows, but there's other ways to think about this. So let's just remind ourselves what's happened there. I'll do a quick and dirty proof that the lower critical dimension is equal to 1. This is sort of a sloppy version of Peierls' argument. Did I do Peierls' argument at the start of class here? I forget. I think I didn't. So let's just imagine we're in one dimension and look at thermal defects. Okay, so it's kind of like it's almost like a perturbative argument in temperature, like a beta, like a low temperature expansion or something like that. So let's just consider a 1D system with a lowest energy excitation and estimate that energy and the entropy of that excitation. So the lowest energy excitation is what's called a domain wall. So you have all your Ising spins. You assume it's a nearest neighbor Hamiltonian. Then, it wants to be ferromagnetic at 0 temperature. But the lowest energy thing you can do is for one term in that sum, right? So like one term in SZI plus 1 is to break that bond. Right? Because that's what the Hamiltonian is. It's a description of nearest neighbor bonds. And so that's called a domain wall. And it has an energy. So the change in energy in the system, which is the energy of the excitation, I would say, minus the energy of the ground state. It's just that bond term here, so it's just basically a constant. But if you imagine this domain wall in higher dimensions, then if it extended just in one of these planes, say, or one of these dimensions, I would imagine this would go as L to the d minus 1. So I think in that, so it would be 2j, right? So you're changing things by 2j L to the d minus 1. which reduces when D is 1, right, to just something like 2J. Let's just keep this in there to keep things general. That's the energy, 2J. What's the entropy? So in one dimensions, the entropy, it's like the configurational, I don't know, all the different ways that you can configurationally change that domain wall. So you have to ask, what's the number of accessible microstates, which have a domain wall? That's one way of thinking about it. And then the entropy is log of the number of microstates, or something like that. So the number of microstates for a domain wall is just the number of positions. You could have put that dotted line. It's as simple as that. And in general D, it could be at any position along one of the axes. The D axes. So just for a domain wall in any dimension, the entropy call it S. So it's log. You can also pick how many, there's a freedom in L, and then there's the different dimensions possible for this. So the number of possible partitions is L to the D. Doesn't matter. I mean, it gives you some constant times log L, which is important. So the free energy is very simple argument. It's not quite correct, or I'd say it's not correct in many ways, but the domain wall isn't actually your lowest energy excitation in principle in higher dimensions. In 1D, yeah, you could have 2, you could flip it back, blah, blah, blah. You have the size of that region. In higher dimensions, you actually want to form little droplets. You don't want to form a big domain wall. So that's Peierls' argument is just a refinement of this argument. But the point is, however you want to, what you're doing is, estimating the delta E for sort of the lowest energy excitation. Because you want to argue that thermally you get these low energy excitations. You're asking whether or not they proliferate. What you need is a balance of that delta E and TS, okay? So whatever functional form, the way you look for a lower critical dimension is basically asking whether there's a balance between these two pieces. So so in one dimension, the energy is just a constant. Okay, and for any finite temperature, right, this term can win because it can be made arbitrarily big by L. That's kind of the logic. And so what it means is you want to increase all that entropy, and all those domain walls will proliferate. So it's an argument about proliferation of the lowest energy excitations. So Oops. Oh, so for D equals 1, entropy dominates. Let's just leave it at that because the energy term is constant of an excitation. For D greater than 1, then you have a balance. You know, at low temperatures, energy cost dominates. So it wants to order things. Energy cost dominates. So that's the lower critical dimension. It's just a sketchy argument for it. If you do Parrell's full argument, the entropy form actually has to change in higher dimensions for all these droplets. But it doesn't matter because all I want to do is contrast this idea that D equals 1 is the lower critical dimension for Ising with what happens in the continuous case. So let's do the same kind of rough logic. Again, I just want to show it roughly. I just want to motivate this. Yeah.
What happened to the D and entropy?
Oh, it pops out front here. So it's just a constant. Yeah.
For your definition of the LCD, you say it's the dimension below which the phase change disappears. Should it be
at which? Did I write below which? I'd say at for this one. So at, you know, the exact dimension, so it's going to move up now, is kind of the tricky case. It's just like the upper critical dimension 4 is a little tricky because you have all this, it's kind of marginally this logarithmic stuff. So I think strictly speaking it's at, but you have to be careful, and that's why Kossler-Salas is important for the continuous case. So in the continuous symmetry, you know, we're not just Ising, right? Let's just imagine we're O2 somehow. You have all these angles. A domain wall's high energy in principle because you can just barely move. You know, you can just have an angle between spins. You know, that's barely moving. And you can imagine energy going as somehow, or energy cost, or the Hamiltonian having like a cosine theta term in it. Something like that. So a domain wall could be, like if you want a domain wall between all spins up and all spins down, you could have a continuous deformation of the spins. So weird. Okay, let's do that. All right, that's not perfect. There's some length scale now over which I've smeared out this domain wall. Call it A. You still have a lattice spacing, which is A2. What you need is the same energy cost, sort of. You want to do the energy entropy balance. So Just do it real rough and quick. You just want to kind of see the, what do I call it, X, dimensional dependence. A, if I have this in higher dimensions, again, LD minus 1. So the excitation, so imagine now I'm costing myself something like cosine, I'm just imagining a Hamiltonian, theta over A, where theta is that total angle, so it's going to be pi in this case. I need a length scale, yeah, so it's A over A, something like that, minus, where if there's no domain wall, everything's aligned, I'm just going to say it's cosine theta, minus cosine theta, so it's 1, A to the L, D minus 1. Okay, I just cooked that up. Theta is this total angle by which the spins have moved. So why it's theta small a over big A, that's like that theta shared between all the nearest neighbors. Okay, and that obviously depends on whether you're O2 or no 3 and blah, 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 but let's just use cosine. You can have other degrees of freedom for higher symmetries. Okay, so my delta E. A is the lattice constant, big A is the domain wall thickness. And let's assume that that argument is small, right? So that neighbors aren't, so it's kind of like a low, expect this to be lower energy than just having a big jump between nearest neighbors. So theta A over A. So we can expand the cosine, that's why I used it. So your delta E would be inverse size of the domain wall, L to the D minus 1. Again, I just kind of wanted to cook off that dependence on A. So, if you just have nearest neighbor, question?
I was wondering, why do elementary excitations are not just like singles being like the very small angle excitation in individual spins as opposed to like a spin wave that you have
like why not back and forth?
Just one.
Just one?
One spin, yeah. Why is it like higher excitation than this? I mean, from this argument.
Why do you want a domain wall, basically?
Why do you want to kind of?
So I think, so let me think of a counting argument for that. So if you just have one spin that's tipped over, okay, so.
Slightly though, the theta can go as small as possible.
Yeah, so that energy goes to 0 as a function of L go to infinity. Maybe that's why.
Well, should it not depend on that? Because it's like.
Well, so that's just a constant energy then. Yeah, it's just a single constant piece. Right.
So you don't care about that.
So, I mean, in principle, you don't care about it because there's we're constructing a scaling argument on the L dependence, right? So the point is that if you take L to infinity and there's log L entropy, or there's L different ways of constructing microstates, then it's like a scaling argument. So this is just I'm just doing a really rough scaling argument here. And we're going to do this exactly, but I'm just telling you the answer ahead of time. So we know what to expect. I don't like suspense. But yeah, I think physically, spin waves are the lowest. Like we can, A post, whatever it's called, argue that spin waves are the lowest energy excitation in these things. Long wavelengths. But I think you can kind of see here, like the energy cost is minimized by making the domain wall as big as possible here. So if you make A go to L, right? Because it's 1 over A. So if you make A big, and if you make A the size of the system, then that's the lowest energy. So that's another reason to do it. You can minimize that energy cost, right? But you have to assume that there's, or you're basically isotropic and homogeneous and nearest neighbors. And so, but under all these assumptions, it makes sense to make A of order of the system size. Can't get any bigger. So then your delta E, L to the D minus 2. And then assuming that your entropy doesn't change, which all you have to assume is that there's some functional dependence of the entropy on L actually, right? But it doesn't matter. Then your free energy will be L to the D minus 2 minus what T log L say? So just by analogy, then the lower critical dimension for continuous symmetries, and this is essentially an O2 symmetry. So it's the lowest symmetry, continuous symmetry, is so lower critical dimensions 2 here. That's the only time you start getting an energy entropy balance. So this is basically just a demonstration of the Mermin-Wagner theorem. And we'll look at the Mermin-Wagner theorem like precisely, or more precisely in the Landau-Ginzburg-Wilson theory. So it's like continuous symmetries, for dimensions 2, 1 or 2, you can't have any ordering phase transition for any finite temperature. So it's the same in the one-dimensional case. In the 1D case, for the Ising model, the only time you really have ferromagnetic order is when temperature is strictly 0. So in the continuous case for dimensions 1 and 2, the only time you have long-range order is when temperature is strictly 0. the range of interactions is really important here. So let me just say this strictly requires short range interactions. But it's good to remember this basically statement because it's on all our quals. And so then the only kind of exception is that in D strictly equal to 2, you have to be careful because there is a phase transition. In D equals 2 or O2. There's a phase transition, but it's not a transition in some long wavelength theory like we're developing here. Again, you need some sort of topological considerations, and that's the Kosterlitz-Thouless transition. So if we can get to the Kosterlitz RG equations, then I'll be happy and we can stop this class. But I'm stopping for today because I'm hungry, so let's meet again Wednesday. And here's your assignment 4, which is due March 17th. And I'll have one more assignment after that one. Questions on this stuff?
So, how can we get the same entropy in the continuous? I think you use the same.
All I said is all you need is a functional dependence on L. Because you just need to have a balance, right? So you just don't want it to be a constant. But there's gonna be some functional dependence, but it's actually just not, it's not strictly log L. And again, you got to think about droplets, not just domain walls, and so that's not.
If A is L, that means it slowly changes from the beginning to the end, right?
Yeah.
How can you count the
Well, you can-
configuration to calculate that?
You can change the beginning angle, so that's one way to get entropy. But that's actually a continuous degree of freedom.
Position of the beginning angle, isn't it?
Yeah. So that's one way of thinking about it. But actually, you got to be careful because it's, in principle, infinite.
Yeah, it's infinite.
Yeah. So I just didn't want to get into that.